A charged particle of mass 0.6 grams and charge 8 nanocoulombs is suspended by a thread. Directly below it, at a distance of 2 centimeters, there is another particle of charge minus 12 nanocoulombs glued to a table. In the first part of the problem, you need to find the tension in the string. So let's draw what the problem gives us. We have a particle that is glued to the table and another particle that is suspended by a string. These two particles are both charged with opposite charges, therefore there will be an attraction force between them. We need to find the tension in the string. For that, let's first draw all the forces acting on charge Q1. We have the force of gravity oriented vertically down. We have Coulomb force of attraction between charge 1 and charge 2, also oriented vertically down. And in the string we have the tension force oriented vertically up along the string. Since charge 1 is in equilibrium, the sum of all forces acting on it has to add up to 0. But as you can see, this is a vectorial equation, which means we need to determine what is the positive direction for us. And for this problem, I will choose the positive direction as being vertically up. That means that the electric force is negative, the force of gravity is negative, and the tension force is positive, and all three of them have components only along the vertical axis. From this equation, we can write that the tension will equal the sum between the electric force and the force of gravity. So all we have to do is calculate these forces. The electric force from Coulomb's law is calculated as the electric constant K multiplied by the product between charge 1 and charge 2 and divided to the distance between them squared. We have all this information, so the electric force will be equal to, the electric constant is 9 times 10 to the 9, charge 1 is 8 times 10 to minus 9 coulombs, nanocoulombs is 10 to minus 9 coulombs, charge 2 is 12 times 10 to minus 9 coulombs, and please observe that I did not use a minus sign here because I have already taken into consideration the direction of this force as being oriented vertically down because the two charges attract each other. Divided by the distance between the two charges is 2 centimeters or 0.02 meters. Don't forget to square it. Using a calculator, you get that the value of the electric force acting on charge 1 is 2.16 times 10 to minus 3 newtons. How about the force of gravity acting on charge 1? Well, force of gravity is mass times gravitational acceleration. The mass of charge 1 is 0.6 grams or 0.6 times 10 to minus 3 kilograms multiplied by, and for ease of calculation I have taken g to be 10 meters per second squared instead of 9.8. So the force of gravity is 6 times 10 to minus 3 newtons. All you have to do in order to find the tension is add up the electric force and the force of gravity, and you get that the tension in the string is 8.16 times 10 to minus 3 newtons. Now for the second part of the problem, we need to find the speed of particle 1 after the string is cut and the particle has traveled 1 centimeter. So what we have here initially is the particle at position A when it is suspended by the string. When the string is cut, the tension in the string disappears and the particle starts moving towards particle 2, which is glued on the table. It moves under the action of the electric force and the force of gravity. After it travels 1 centimeter, so basically it's halfway between the initial point and the final point, we need to find the speed. So let's consider that point to be point B. Speed is related to kinetic energy. So all we need to do in order to find the speed is find the kinetic energy at point B. Kinetic energy is related to the work done by all the forces acting on the particle when it is moving from position A to position B. So we are going to use the work kinetic energy theorem that says that the net work done on the particle when it moves from position A to position B equals the change in the kinetic energy of the particle, or kinetic energy at B minus kinetic energy at A. Now the net work in our case will be equal to the work done by the electric force and the work done by the force of gravity. These are the only two forces acting on the particle. I would like to remind you that if the force is constant, the work is calculated as the dot product between the force and the displacement of the particle. And if the force is not constant, you have to take the integral of the dot product between the force and the displacement. From the two forces, the electric force changes with distance, therefore the electric force is not constant, but the force of gravity is constant as the particle moves from A to B, because it depends only on the mass and the gravitational acceleration, and both of them are staying the same. So in order to calculate the electric force, I have to use the integral, and I will write then that the work done by the electric force equals the integral from A to B of the dot product between the force and the displacement. Now I want you to remember that we have chosen the positive direction upward and the particle is moving downward, so the angle between this will be 180 degrees. The dot product depends on cosine, so cosine of 180 is -1, and that's where I have this minus in front of the integral. And the integral will be from the initial position to the final position of the magnitude of the first force, of the force of the electric force, which is kq1 q2 over the distance squared, multiplied by the distance. K, q1, q2 are constants. They go outside of the integral. And then I have that the integral that is left is integral from the initial position, which is the position of point A, to the final position, which is the position of point B, of dy over y squared. That is a very easy to solve integral, and the value of that integral is -1 over y between the limits of integration for the initial and final position. And if you put the limits of integration in and you multiply all the values given for the electric constant k, the charge q1 and the charge q2, you get that the electric force does a work equal to minus 864 times 10 to minus 9, this is the value of these three quantities multiplied together, multiplied by minus 1 over the final position yb, which is 1 centimeters from the table, minus minus gives you plus 1 over the initial position, which is 2 centimeters. Using a calculator, you get that the work done by the electric force is 4.32 times 10 to minus 5 joules. Now, the other work is done by the force of gravity. Force of gravity, as we said, is a constant force. Once again, force of gravity is oriented down and the displacement is oriented upwards, which means that the angle between these two, when you calculate the dot product, is 180 degrees, so you have a minus sign in front. The displacement of the particle is nothing else than the final position minus the initial position. So I will have that the work done by the force of gravity is, the mass is 0.6 times 10 to minus 3 kilograms. The gravitational acceleration g is 10. Final position is 0.01 meters. Initial position is 0.02 meters. Using a calculator, you get that the work done by the force of gravity is 6 times 10 to minus 5 joules. Now all you have to do is add up the work done by the electric force and the work done by the force of gravity in order to find the total work or the net work done on the particle when it moves from position A to position B. And the net work in this case will be 10.32 times 10 to minus 5 joules. Okay, we found the net work. Now, in order to find the speed at point B, I need to figure out what is the kinetic energy at point B, and for that I need to know the kinetic energy at point A. But when the particle is at point A is exactly at the moment in time when the string is cut, so the kinetic energy at A, which is 1/2 mass velocity at A squared, will be equal to 0 in this case because the velocity at point A is 0. Charge 1 is stationary just before it starts falling. So all I have left from the work kinetic energy theorem is that the net work equals the kinetic energy at point B. Well, kinetic energy at point B is 1/2 mass velocity at point B squared, which, if we replace the mass, will give us 1/2 multiplied by 0.6 times 10 to minus 3 velocity at point B squared. We make this value equal to the net work, which is 10.32 times 10 to minus 5 joules. 0.6 times 10 to minus 3 divided by 2 is 0.3 times 10 to minus 3. And from there we find that the square root of the speed at point B is 0.344. Taking the square root of that value, you get that the velocity of the particle after traveling 1 centimeter towards particle 2 will be equal to 0.58 meters per second.